Hello, everybody. Today we're going to talk about the foundations of mathematics from a computational perspective. So, in fact, the foundations of computer science has been influenced by this question of what's the foundation of mathematics? Can we base mathematics on clear foundations? And kind of when we are in school, right, and we learn this basic math operations like that 7 times 8 is 56. And we don't ask ourselves, what does it mean? What is 7? What is 8? Why are they 56? And later on, we learn about axioms and we learn about derivation and we learn about various kind of mathematical systems. And the question that excited mathematicians was to base all of mathematics on clear foundations, on a mathematical system with some good properties. And today we'll talk about why this hope cannot be obtained, and our perspective will be based on computation. So what is a formal system? What's the formal system that we want to have? Formal system is like a language. It allows us to write finite mathematical statements. It has a definition of what's true and what's not true. And it has a definition of what is a proof. What is a proof of a statement, right? We want mathematics to be able to specify statements, to argue about whether they are true or not true, and to have proofs for statements. So let's give an example. The example is that every Turing machine does define some formal mathematical system over all strings. And every string W would represent a mathematical statement that M accepts W. The true statements are all the strings that M accepts, meaning the language recognized by M. And a proof that M accepts W can be defined by a computation history on M on W. So a computational path of M on W that accepts. So this is an example of a mathematical statement. It's not a coincidence that I'm using Turing machines for that. Now, the way I described it, I described ways of arguing about things that are true. I didn't describe how to prove that a particular statement is false, and this looks like the system has its limitations. It's not perfect. So what we'll do is try to define what would make a formal system. What are some basic requirements from a formal system that will make us happy, and then we will show that you can't always get what you want. So what we want is first that the system will be interesting. So let's define a formal system to be interesting if mathematical statements that can be described in English, or precisely described in English, should be expressible in this system. Right? If we want to base all of mathematics on this formal system, we want to be able to express whatever we can already express in English and to express it in a formal way. Another thing is that we want proofs to be convincing. So we want a way to verify that the proof is correct. Otherwise, it's very easy to have a formal system where the proof will just say, yes, it's correct, but we cannot necessarily verify it. And finally, we also want whenever there is a proof that can be, again, precisely described in English, it should be expressible in F. right? If we are going to kind of transfer all of our mathematics from English or whatever other language we choose to this formal system, then we need to be as expressive, both in defining what are, in defining mathematical statement, in describing proofs. So let's give kind of an instantiation of this using our computational lens, using Turing machines, and now we can define a formal system F to be interesting if, again, we wanted any mathematical statement that can be expressed in English to be described as a statement in F. So this in particular should mean that given any machine M and string W, there is a computable statement. So we can specify the statement SMW in F, where SMW is true in F if and only if M accepts W. So the statement M accepts W is something that we can describe in English. I just described it, and the entire course actually described it, defined what is a Turing machine, defined what is acceptance. So we can express this this statement in English. We want to express it in F. Now, this doesn't sound like all mathematical statements. We will be happy only with these mathematical statements and their negations. And but if we believe Church-Turing thesis, this is a pretty rich family of statements. So we're not giving much by restricting this in this way. Proofs are convincing. So now we have the language of saying what does it mean. So there is a Turing machine that can check that a proof of a theorem is correct. In other words, the set of pairs S and P, where S is a statement in F and P is a proof of this statement in F, this set is decidable. So we should be able to, given a proof, to verify its correctness in F. Right, this is what we expect. And again, it's well, here it's a pretty mild requirement. We only require decidability. If we really wanted to do something with this formal system, we would probably want some efficiency measure. But let's put it aside. And finally, we want to say that any proof that can be described in English should be expressible here. And so for every statement SMW that is true, there is a proof in English. This is just the computational path, as we said, accepting computational paths. So we want it to be the case that there is also a proof within this formal system that of the statement SMW, the statement that M accepts W. So we instantiated what we meant by interesting formal system with properties from computation. Now, being interesting is not interesting enough. We want more. And the first thing that we definitely want is consistency. So a formal system F is consistent or sound. This is a different way of saying it. If no false statement is a valid proof in F. So proof in F implies truth in F. If this doesn't hold, then really the system is not really great. And in fact, we can again have a trivial system. Finally, what we want here, and it will seal the deal, and create our impossibilities is that a formal system F is complete if every true statement has a valid proof in F. So truth in F implies a proof in F. And in fact, we would have loved to have that. And furthermore, we would have loved to be able to automatically find. So we want it to be the case that there is a proof for every true statement, and in fact that we can find this proof efficiently. So then everything is great, and all of mathematics is in the tip of our hands, the fingertips of our hands. But there are limitations to mathematics, and we'll have these three theorems. So for every consistent and interesting F, first Gödel theorem is that F is incomplete. There are statements that are true but have no proof. There are mathematical statements in F that are true but cannot be proved in F. And furthermore, the second theorem is that the consistency of F itself cannot be proved in F. So here is a very interesting statement about F that we would have liked to prove. It's a mathematical statement, and this statement doesn't have a proof. So it's not only that there is some proof, some statement perhaps not interesting that cannot be proved, but there is a very interesting statement that we cannot prove. And finally, kind of Church-Turing showed that the problem of checking whether a given statement F as a proof is undecidable. So there are true statements that don't have a proof. And so we'll say, okay, at least let's find all the statements that have a proof. But we cannot even hope to do that. So given a statement, we don't necessarily even know if it has a proof or not. So let's give a little bit about all of them. These are confusing statements as kind of proofs, and you can read more about them. But from my point of view, what I really want you is to understand the statements. And I mainly want to do it because it's part of what being an educated computer scientist mean. And not that we'll do much with these statements, but I want you to be aware of them. And so that's the level of understanding I'm expecting. If it's confusing, don't worry about it. It's confusing. If I'll get through the video without confusing myself, it will already be an achievement. So don't worry about it. So let's start with the first Gödel theorem. Every consistent and interesting F is incomplete. There are true statements that cannot be proved. So we have these special statements that we like. SMW in F is true if and only if M accepts W. So let's prove this Gödel theorem. And let's define a Turing machine G. And now that we know the recursion theorem, we can assume that G can obtain its own description, right? So let's use it. It will make our life easier. So the first thing that G does is obtain its own description. And now using its own description, it can create this statement S prime, which is the negation of the statement SG epsilon. The statement SG epsilon is that G accepts the empty string. And so the negation is that G doesn't accept the empty string. This is the statement S prime. Now, what does G do now? It's going to search for a proof of S prime in F over all finite length strings. So it's going to enumerate all finite length strings, let's say in lexicographic order, and check if any of them is a proof of S prime in F. And it's going to accept if a proof is found. So If a proof exists, then it's going to be found, and it's going to accept. Let's see what's going on here. The claim is that S prime is true in F, but has no proof in F. So S prime can be true or false. Let's see what happens if it's false. We'll get a contradiction. If it's false, what does it mean? So S prime is false. It means that that SG epsilon is true, right? S prime is the negation of SG epsilon. And SG epsilon means that G accepts the empty string. What does it mean that G accepts the empty string? For G to accept, it has to find a proof of S prime. That's the only it accepts. It means that S prime is true, and it means differently that it didn't accept. Why? Because the system is consistent. We don't have proofs of false statements. So if S G epsilon is true, then there is a proof that it is false, and therefore it is false, which is a contradiction. And so the only other option is that S prime is true. But now, what would happen if there is a proof that S prime is true? If there is a proof, then at some point G would find this proof and accept. And then it will mean that S prime is false because G did end string. So if S prime is false, we reach a contradiction. If it is true and there is a proof, we also reach a contradiction. So the only option is that S prime is true, but that there is no proof. So S prime basically says there is no proof of S prime in F. Okay, that's the first one. The next one will be a little bit more confusing, so be ready. So the next one is that the consistency of F cannot be proved within any interesting consistent F. So if F is consistent and interesting, then its consistency by itself cannot be proved. So suppose we can prove, so for the sake of contradiction, suppose that we can prove that F is consistent in F. We constructed in the previous slide a statement not SG epsilon, which means G does not accept epsilon, the empty string. And we showed that this statement is true, but has no proof in F. So that's what we showed before. Now, G does not accept epsilon, if and only if there is no proof of not G epsilon in F, right? What G does is to search for a proof that of not G epsilon, not S G epsilon. And if it finds a proof, then it will actually accept. So if it does not accept, if and only if there is no proof. But if there is a proof, F is consistent, then there is a proof not SG epsilon. And this will create a contradiction because we just argued that there is no proof of not SG epsilon. So again, we're going to show that if we have a proof that F is consistent, then we also have a proof that not SG epsilon, and this is a contradiction. So this think about that as a proof of the statement, not SG epsilon in F. Very high level. There's lots of details to complete. So the proof itself is a proof by contradiction. If SG epsilon is true, so we assume that SG epsilon is true, And when we'll reach a contradiction, we'll deduce that not SG epsilon. Then there is a proof in F of not SG epsilon, right? If SG epsilon is true, then just by the way we defined SG epsilon, by what we proved here, and then there is a proof in F of not SG epsilon, because what G does is to search for this proof. So if G halts on epsilon, it means that there is a proof of not SG epsilon. And now F is consistent, and therefore not SG epsilon is true, right? Because if there is a proof of that, then if there is a proof of not SG epsilon, then not SG epsilon is true. But SG epsilon and not SG epsilon cannot both be true. Therefore, not SG epsilon is true. So this is a proof by contradiction that not SG epsilon is true. And the one ingredient that we actually used within it is a proof that F is consistent. This is what we used here, right? Just the fact that there is a proof in F of not SG epsilon doesn't say that, doesn't prove that not SG epsilon is true, because, and also for SG epsilon and not SG epsilon, the fact that both of them cannot be true relies on the consistency of F. And this is an ingredient within this proof. So given this ingredient, what's here is a complete proof within F of not SG epsilon. And that's a contradiction, because we said that there is no proof of not SG epsilon. So because there is no proof, then this cannot be a proof. And for this to not be a proof, we need the fact that F is consistent not to have a proof. Are you confused? I'm pretty confused. You can read more about it more slowly, but I'm okay with your confusion, and I won't expect you to understand the actual proof, but I do want you to understand the theorems. The final thing, the final blow to this program of basing mathematics on a firm foundation, and perhaps also automating it, is the following: that just to separate whether there is or isn't a proof for a statement is something we cannot compute. It's not even decidable, not even that it cannot be decided efficiently, it cannot be decided at all. So the language provable F of all the statements that have a proof in F, all the statement S that there is a proof in F of S, or there is a proof in F of its negation, and this language is undecidable. So let's prove that. Suppose provable F is decidable. It means that there is a Turing machine P that decides it. And now we can decide ATM using the following procedure. On input MW, we're going to run P on input SMW. So recall SMW is a statement, is a mathematical statement that M accepts W. Now, if P accepts, then there is it means that there is a proof either of SMW or its negation. And so we can search in parallel for a proof both for this statement and the other statement. We can enumerate lexicographically all proofs and check them, each one of them is a proof both for either for SMW or for its negation. And if P accepts, it means that there exists one of these proofs. We're going to find it. And based on it, we can accept or reject. So if we found a proof of SMW and then we can accept, because M accept W. If we found a proof of its negation, then because of soundness, we can again reject. And finally, if P rejects, it means that there is no proof of S or its negation. And I claim that then we can reject. I think that I claim that we can reject because if M accept W, then there is a proof that M accepts W. This is just the thing we said a few times in this video, that the W is a proof that M accepts W. So why does it work? I just told you, but you can think about it some more. So there you have it. Lots of very disappointing things. So what we saw is that if a formal mathematical system is consistent and interesting, then there are truth statements that cannot be proved, including a very interesting one, which is the consistency of the system. And provable statement we cannot tell that are provable. And I leave you with this question about what about statement with short proofs? So we know that in general, just we cannot tell if there is a proof of a statement, but can we tell that there is a short proof? Assuming that there is a short proof for a statement, can we tell that? This will definitely be decidable because we can enumerate all short proofs, but depending on what short actually mean, this will give us the different way of viewing the P versus NP problem. The P versus NP problem is whether there is a way to decide efficiently if there is a short proof for a statement. Thank you.